Hello students, welcome to classroom. I hope you are all doing well. Continuing with the class, today our topic is atmospheric refraction. This topic comes after dispersion of light through a prism. So we have already covered dispersion of light and then we also discussed the formation of a rainbow. After that comes this topic, and this topic is a very important topic. In this topic, we will be learning about refraction again, but this time we will be studying refraction, which is bending of light, which happens because of our atmosphere. Okay, previously we have discussed about refraction through lens, refraction through prism. Okay, now today our topic is refraction through our atmosphere. So this is a very important topic, and it is not very difficult also. So we have to understand this topic. By understanding this topic, there are some very important phenomena in this world which you will understand. For example, by understanding atmospheric refraction, you will understand the twinkling effect also. By understanding atmospheric refraction, you will know about the actual position and the apparent position of the heavenly bodies. So these things, okay, and also the time delay, and also when does the actual sunrise takes place and when does the actual sunset takes place. So these are certain things which this topic teaches us and which we learn from this topic. So this lesson is very important. So without much delay, let us go and start the topic and understand together what actually atmospheric refraction is all about. So atmospheric refraction. We know that refraction is bending of light. So refraction is bending of light. Now, but in today's topic, we will be talking about atmospheric refraction. That means bending brought about by atmosphere. So does our atmosphere bend light? That is a good question you can ask yourself at this moment. Okay, and reminding, okay, my dear students, to grab a book, a pen, okay, or a pencil, and draw and make notes out of these explanations. Okay, it will be very helpful for you all. So back to the question. So does our atmosphere bend light? Does our atmosphere refract light? What is the answer to this question? The answer is a yes. Our atmosphere bends light. Our atmosphere refracts light. So the answer is yes. So now let's try to understand how. So how? Okay, how does, okay, our atmosphere, how does our atmosphere bend light? So how does our atmosphere bend light, or even why? Okay, it can be how or why. Okay, it will work both ways. Okay, how does our atmosphere bend light, or why does our atmosphere bend light? Now, in order to understand this, let us understand this thing. So let's say this is okay, let me draw here. So let's say this is Earth. So this is our Earth. Now our Earth is covered by a thick layer of air which we call the atmosphere. Yes or no? Yes. So we have atmosphere which covers our Earth. The moon has no atmosphere, okay, but our Earth has got atmosphere. So the layer of air which covers the Earth is called atmosphere. Now, interesting fact about our atmosphere is that the composition of our atmosphere is not same, and also the density of our atmosphere is also not same. Very important, I repeat, the density of our atmosphere is not same. Remember class, air is densest near the surface. This is the surface, okay, this is the surface, this is the land, okay, this is the land, okay, and we have air, okay, surrounding the Earth landmass. So we have air here, okay, so we'll draw the air now. But remember this, before I start drawing, that air is densest near the surface. That means there is more air particles, okay, there are more air particles near the ground, okay, and the density of air keeps on decreasing as you go higher and higher, okay, and finally you reach space. and space has got no air. Okay, and as you enter from space down to earth, okay, the density of air keeps on increasing. Okay, but as you exit from earth, as you escape to space, what happens? As the rocket goes higher and higher leaving earth, the density of air keeps on decreasing, and finally it reaches the outer space. I hope this is clear. Now, so let me show. Okay, let me just draw like this and explain to you. So let this be these are the layers of atmosphere. I will not draw much. I'll just draw three layers. So like this. Okay, so these are the layers of atmosphere. I have drawn here 3 layers: layer 1, layer 2, layer 3. Now remember, layer 3 is the densest, layer 2 is second most densest, and layer 1 is the least denser of these 3. And then outside, this is what? This is space. Okay, class, we are discussing about our own earth. We are discussing about our own earth here. Okay, not any foreign planet, but our own earth here. So now this is the atmosphere. This is our atmosphere. This is our atmosphere, which has got variable composition. So our atmosphere the answer to this question, okay, is our atmosphere has variable composition. What does this mean? This means that the composition of our atmosphere is not same, rather it is different. Okay, so it is different. Most of the air particles are here, okay, in the troposphere, okay, near the ground. Then here you will have air particles, but then here its composition, its density will be less compared to this layer. And even here you will have, okay, but its density will be lesser than this, and even more lesser than this. Okay, likewise. So this is a rough picture which you have to understand, okay, if you want to understand atmospheric refraction. Now remember, so see, all of these 3 will act as a medium now. It's air, okay, it's atmosphere. Atmosphere is made of air, and light can easily pass through air. So air is a medium. That makes atmosphere also a medium. After all, okay, our atmosphere is made up of air. Yes or no? So now, okay, now let me draw a star here. So let me draw a star here. So let me draw a star here. Okay, so this is a star. Now stars are luminous bodies. That means they emit light from their own body. Our sun is a star. Okay, remember, you already know that. So our sun is also a star. Okay, so stars, they produce their own light. So now this star, let's take a ray of light coming from this star. So let's take the ray of light. So in space there is no refraction. Okay, class, in space there is no refraction. So in space the ray of light will travel straight. So let us make the ray travel straight like this. Okay, so this is the ray of light. Okay, a ray of light traveling in space. Okay, this is a ray of light. So this is a ray of light, light ray. This is light ray coming from the star. Okay, now what will happen? Now it has made contact with the atmosphere. Okay, so now refraction will take place. Up till here there was no refraction because it was in space. Okay, now it is making contact with the atmosphere, so there are some particles here. So now medium change has taken place. Okay, this is rare. Okay, now it will enter to a denser medium. Okay, so what will happen? Bending will take place. So this ray will undergo bending. So let us bend the ray. So it will go bending. Okay, it has bended a little. Okay, then again, compared to this medium, this is more denser again, so it will bend more again. So it will bend more. Okay, then compared to this, okay, compared to this medium, this medium 3, layer 3 is more denser than medium 2, so more bending will take place. Okay, so this is how the light, okay, the light travels, okay, down to earth. The journey of this starlight down to earth will not be straight. Okay, it will never be straight. Why? Because we have atmosphere. If there was no atmosphere, then yes, this ray will travel straight. It will go somewhere here. Okay, it will be somewhere here. But then since we have atmosphere, that is impossible. Okay, when light passes through the atmosphere, it will undergo bending. Okay, I hope we are all clear with this. Okay, now let's say there is an observer here. So let's say there is an observer here. So the observer is here. Okay, my famous drawing. Okay, and this light ray enters to the eye of the observer. So this is the observer. This is the observer, which is down here on earth. It can be you, it can be me. Okay, it is us. Actually, it is us humans only. Okay, it is us humans only. So now this light ray enters our eye. Again, now remember class, our eyes can only see straight. Okay, our eyes can only perceive straight light rays. Okay, so our eyes can only read straight. So how will our eyes perceive this? How will our light ray, or how will our eyes see this? Okay, how will our eye see this? See the image. Okay, it will only see straight. So our eye will see it straight. Okay, I have to make it straight. Yes, so our eye will see the image of the star to be here. Okay, so the light ray, it enters, it bends, and then it enters our eye, and our eyes can only see straight. So okay, according to our eye, the image of the star will be from here. So for us, this is the star. Now you check out. This is the actual position of the star, and this is, okay, the position which appears to us. Okay, so this is the position, okay, which appears to us. So to an observer, the star is here at this position, whereas in reality the star is here. So this is the actual position of the star. This is the actual position. This is the actual position, and this is the apparent position. This is called the apparent position. This is the apparent position of the star. Why apparent position? Because this is the position, okay, which we see down here on earth. So the star for us down here on earth is here. Okay, whereas in reality the star is actually here. That's why it's called apparent position. This is never the actual position. This is the apparent position. The actual position is below the, remember, the actual position is always below the apparent position. So the actual position is below here. Okay, this is a fact, remember. Okay, the actual position is below the apparent position. So there is a question like, what do you mean by apparent position? So the answer to this question is, the apparent position is the position which appears to us, okay, to an observer down here on earth, okay, by the refracted light rays. Okay, so the refracted light rays, they enter the eye of the observer, and the eye of the observer perceives an image of the star. Okay, the image which is perceived, okay, in the eyes of the observer, this is called the apparent position. Okay, so basically it is the position which appears to an observer down here on earth, okay, brought about by the light rays which have passed through the atmosphere and has underwent refraction, which is bending. I hope it is clear. Okay, now to an observer here on earth, it appears like that. But what if this observer goes out? What if he goes out to the space? So now he is here at space. Okay, so now if he is here, then what happens? The light rays, they travel straight to his eyes. There is no bending, there is no refraction. So out here in space, he will see the actual position of the star. So his judgment of the star, that the star is here at this point, at this position out in the space, is accurate, is 100% accurate. But for us, or for any person who is viewing the same star down here on earth, our judgment that the star is here is very much wrong. Alright, so remember, this is happening because of atmospheric refraction. This is happening because of atmospheric bending. So I hope it is clear. Okay, it's not very difficult, rather it's interesting, I should say. Okay, now remember class that refractive index. So remember the refractive index keeps on increasing. Okay, so Ri keeps on increasing, so the refractive index, okay, the Ri keeps on increasing as we go down. So from the Ri, so let me write here. So Ri, this is Ri, refractive index, okay, increases as we enter the Earth atmosphere. Okay, refractive index is a measure of the amount of bending. Okay, in case you forgot, Ri is a measure of the amount of bending, is a measure of the amount, I'll just write it in short, of bending. Okay, we have also discussed about refractive index in the previous slides. Okay, in the previous lesson, light and refraction, so you can always go and visit. So there we have discussed in detail refractive index. So in simple terms, refractive index is a measure of the amount of bending. Okay, so how much light will bend when light travels into a particular medium. Okay, that is calculated in refractive index. So here, okay, light ray, okay, bends a little here because the medium is comparatively rarer here, but light will bend more in medium 2 because it's more dense here. Okay, so the Ri of 1 is least here. Okay, the Ri of 2 is more than 1, and this is the densest, medium 3. Okay, layer 3 is the densest, so here light will bend more because the atmosphere is densest here. So Ri of layer 3 is the highest. That's why Ri keeps on increasing. So the refractive index, okay, increases as the light ray, as we move downwards to Earth. Okay, and as you move outwards, what will happen? The Ri will decrease. So here, highest Ri, then this layer, okay, highest Ri is here. Okay, then this layer will have little less Ri, and this will have the least Ri, like that, and this is space. Okay, goes on decreasing. All right, so remember, okay, this also, that the refractive index increases, okay, downwards. Okay, means as we enter the Earth atmosphere, as we head towards the Earth, the refractive index keeps on increasing. Okay, this is a very important point you have to understand. So refractive index increases, okay, as we head down to Earth, which means the bending will be more. Okay, as the light ray enters the Earth atmosphere, it bends more and more as it gets closer to the Earth surface or Earth's ground. Okay, so this was atmospheric refraction, and here we have just discussed, the topic was apparent position. Okay, so here we have discussed about the actual position of the star and the apparent position of the star, okay, which we can only understand, okay, by understanding atmospheric refraction. So now the next topic will be twinkling of stars, which is also discussed under atmospheric refraction. So what is twinkling of stars? Now we have all seen stars twinkle. Stars, they come out at night. Well, they are there even during daytime, but because of the sun's brightness, we don't see them. They are up there in the sky. But at night, when the sun goes down, okay, we are able to see the light. Okay, we are able to see the stars. Okay, they are up in the sky. Now stars twinkle, and the reason for twinkling of star, okay, you will study from this topic. So the reason is atmospheric refraction. Okay, so twinkling of star. What will be the other definition of twinkling of star? Do we have other definition by which we can define twinkling? So how do we define twinkling? So what is twinkling? Twinkling of star, na? Twinkling. So twinkling. What is twinkling? See, stars produce stars, they produce light rays, they emit light rays, and then these light rays sometimes, okay, because of the atmosphere, okay, to our eye, sometimes they appear bright, sometimes they appear faint, means less bright. Sometimes they appear bright, sometimes they appear less bright. Okay, so this phenomenon where the brightness of the star, okay, where the light coming from the star, okay, appears brighter to us at one point, then again in the next second it appears faint to us. This phenomenon is what, okay, is called twinkling. Okay, and this twinkling is happening because of atmospheric refraction. So let us go in detail and study, okay, how this twinkling phenomenon is taking place. So to understand twinkling, I need to draw a diagram. So yes, so let us draw the different layers of atmosphere, okay, because our earth has got atmosphere. So let's say this, okay, these are the layers of atmosphere. So layer 1, layer 2, and layer 3. Okay, so this is the layer 1, or let's start from here, layer 1, layer 2, and layer 3. Now let's take a star here. So let's take a star. Now there are many light rays, okay, there are many light rays coming from a given star. Okay, so for our convenience we'll draw some light rays. Okay, so let's draw some light rays, say 1, 2, 3, 4, 5, 6, 7 light rays I have drawn. Now 7 light rays are headed towards earth. This is earth, Now each of these light ray, they will never travel like this. Okay, they will never travel straight like this, rather they will bend, isn't it? Because this is atmosphere, and then we know now that when light enters the atmosphere, they bend. So each of these light rays will bend. Okay, now I have told you earlier that the atmospheric conditions are not same. Okay, now to understand twinkling of star, let us take a different approach. Okay, so let us take a different approach. Now this is all just assumption. Okay, these are not these have not been experimentally verified, but to help you understand, okay, get a picture of how it is, I'll just use an assumption. So let's say, since we know that the atmospheric conditions are not same, and I've already told you that air is densest at near the surface and the density keeps on decreasing. Let's say at a given time, say 10, okay, let's say at 10 p.m. at night, okay, at 10 p.m. at night, let's say the number of air molecules here, let's say it's 10,000. Okay, 1, 2, 3. Okay, like I said, this is just an assumption. Okay, this is just an assumption. In reality, there are crores and crores. Okay, so at 10 it is like this, then at 10:1, which means 1 second has passed. Okay, got it? Okay, at 10 p.m. in layer 3, densest 10,000. Okay, then here let's say layer 2, 9,000. Then at layer 1, let's say 8,000. Okay, now this is the condition of the atmosphere at 10 p.m. Now remember class, this will change. Now at 10:02, so 1 second has passed, just 1 second. Okay, and 1 second is not much time, isn't it? 1 second, it has just passed by. So now in the next 10:01 p.m. these conditions will have changed. Okay, now it will be how much? It can be now say 9,500, changing, isn't it? Now this will have changed to 8,500, this will have changed to 7,500. all right, so this is the condition of the atmosphere at 10:01 p.m. Now at 10:02, what will happen? These conditions will change again. Okay, now maybe it will change to 9,000 here, 9,000 here. Maybe it will change to 8,000 here. Maybe it will change to 7,000 here. So I hope you are getting the point. What I'm trying to tell you, that the atmospheric conditions are not same. Okay, at every point of time they keep on changing. Okay, so you have to first understand this. Okay, now I'm telling you this, and I want you to understand this, because without understanding this, the next discussion will be a little difficult for you to understand. So understand this one, okay? Remember that the atmospheric conditions are not same, okay? By the time we have started this lecture, around 5-10 minutes is going on, okay? Now in this period of time, so many times the atmospheric condition have changed, okay? Just okay, within 1 second the atmospheric conditions will change. So remember, that is how our atmosphere is, okay? It's constantly changing every second, okay? Crores and crores of air molecules are changing. Remember that, okay? So now what happens? 7 rays, we are taking 7 rays. All these are light rays, okay, coming from the sun, from the star to earth. They are headed towards the earth. They have made contact with the earth atmosphere, so now they will enter the earth. So let's take for 10 p.m. okay, at 10 p.m. So let's say at 10 p.m. because of the condition there prevalent, what happened? Let's say this is ray number 1, is not? So let's say it went like this, okay? So it will undergo bending, okay? Let's say it goes like this, then it goes like this, then it will go like this. Let's say your eye is here, there's an observer's eye here, okay? I have to draw in the yes, let's just draw the eye like this. So the eye is here, okay? Our eye is here, the observer's eye is here. I have drawn a big eye, okay? Then this is straight, now it will go bending, okay? And this is called bending. It is straight, it will go bending, okay? It is straight, okay? It goes away, it is straight, and it goes away. So here we see that ray 1, okay, did not make it to the eye. So this ray, I don't know whether it will enter the eye. Okay, it has entered. So this is entering, this is entering, this may not enter. So at 10 p.m. this is the condition, okay? At 10 p.m. out of 7 rays, how many rays entered your eye? 1, 2, 3. So at 10 p.m. 3 rays have entered your eye. 3 rays entered your eye, okay? At that given condition, okay, 3 rays entered your eye. Then let's take at 10:02. At 10:02 the conditions will have changed, the atmospheric conditions will have changed. Now maybe this ray which did not enter your eye, okay, earlier, may now bend, and it may even enter your eye, okay? And their angles will also now change. So now they will have changed their angles, okay? Then even this one will have changed its angle. So maybe it's like this. Then even this one will have changed its angle. Maybe it's like this, okay, like that. And maybe even this one has changed its angle, and then it has entered like this. So now at 10:01, how many? 1, 2, 3, 4, 5, 6. 6 rays. At 10:01, 6 rays are entering your eyes, okay? So now at 10:02, let's take one more example. At 10:02 again the conditions will have changed, okay? At 10:02 the conditions will have changed, and let's say this ray, okay, did not make it again, okay? This ray did not make it again, it went away again, okay? And then even let's say this ray did not make it again, so bended a lot, it went this side. This ray also did not make it, so it bended a lot. Even this ray did not make it, so it bended a lot, okay? Then let's say this also did not make it, and it bended a lot. And let me correct these two now. Let's say this entered and this is wrong, it should go like this, bending, okay? So at 10:02, what happened? 2 rays, hardly 2 rays, okay? We can say 1 ray, I guess, okay? I have been very stingy here, at least 2 rays, okay? Let's say 2 rays have entered the eye, okay? Or 1 ray, I think we cannot count this one. So only 1 ray. So only 1 ray has entered your eye. Now you see, only 1 ray has entered your eye. Even this ray did not enter your eye. Now you see, this is what is happening. Constantly the composition of the atmosphere changes. So in just 3 seconds, you see the amount of light entering your eye, how much it differs. At 10 p.m. when you were looking at the star, so you went up to the terrace and you were looking at the star. Now remember class, if you just spare 1 second and look at the star just for 1 second, you will never see the twinkling effect. In order to experience the twinkling effect, you have to keep looking at the star and sacrifice 10 seconds, 15 seconds, 20 seconds. Okay, so just once looking at the star for 1 second, you will not see twinkling. So you have to look for more than 5-6 seconds, okay? 5-6 seconds to experience twinkling. So at 10, 3 rays entered your eye. At 10:01, 6 rays entered your eye. At 10:02, only 1 ray entered your eye. So now you see, at some point more rays are entering UI, at some less rays are entering UI, at some very less rays are entering UI. So how will the star appear? When more light rays enter UI, the star will appear bright, okay, more bright. And when less rays enter UI, the star will appear, okay, in the next second the bright star will appear dim. Why dim? Because now less light is entering UI. Okay, then again in the next second more light will enter UI, so the same star will appear again bright. So this, okay, this amount of light entering UI keeps on changing. Now why is it changing? Okay, why is it changing? Who is responsible for the change? Okay, the atmosphere is responsible for the change. Okay, maybe there's a slight breeze blowing, okay, at night some gentle breeze, some gentle winds they blow, so they will keep on changing the condition of the atmosphere. Thereby what will happen? The amount of light entering UI keeps on fluctuating. So the light rays entering UI is not constant, they keep on changing, and because of which what happens? The overall picture, the overall image that your eye forms, or what that you see, is a twinkling effect, sometimes bright, sometimes less. So this is how you see twinkling. Okay, this also contributes to twinkling. The other one is the apparent position, and the apparent position, the one which we just discussed earlier. That now let's say more rays. Let's redraw our figure again. So let's say this also enters your eye, then let's say this also enters your eye, this also enters your eye, this also enters your eye, and this two doesn't make it. All right, now your eye will see straight, so your eye will bring the image to be here. For this one it will bring it here. This is all happening in one time, okay, in one time. So now you just look, okay, these are the apparent position of the star. So in that 1 second, see, four apparent positions are visible. Okay, so this is going to create that wavy, hazy phenomenon to the star, which also contributes to twinkling. Okay, so this is how your eye will perceive the position of the star. So this phenomenon along with this, okay, these rays together, they walk together, and then what will it do to you? It will create the twinkling effect in your eyes. So this is the twinkling effect, okay, which is visible to us, or which we see if we look at the stars. Okay, this is how twinkling effect is produced in star. It is all because of atmospheric refraction. So I hope it is clear. Okay, it's not very difficult. Okay, you can rewind the video and watch again. So it is not difficult at all. You just have to understand atmospheric refraction. If you understand atmospheric refraction, this is not very difficult. And remember, to understand twinkling, you have to consider that the atmospheric conditions are not same, because of which the amount of light rays entering your eye are not same. They keep on changing. More light enters your eye, the star appears bright. Less light entering your eye, the star will appear dim. Okay, so now we will move to the next topic. The next topic will be advanced sunrise and delayed sunset. That will be the next topic. So advanced sunrise and delayed sunset, another very important phenomena which is experienced because of atmospheric refraction. So apparent position of the star is also because of atmospheric refraction. Then twinkling effect of star is also because of atmospheric refraction. And finally, okay, the last topic, subtopic on this big topic, which is atmospheric refraction, will be advanced sunrise and delayed sunset. Now let us try to understand this. Okay, this is very easy. So let me draw a figure, many figures to be drawn here. So I will draw our earth. So let's say this is earth. So our earth is here, and then now I will draw another line which is called the horizon. So the horizon is like this. So this is the horizon. This line will be called the horizon. Okay, this line is called the horizon. Horizon. Now what is the horizon? The horizon is an imaginary line, okay, which is drawn. Now this line does not exist in reality. On Earth, above the Earth, you will not, on the poles, you will not find this line. Okay, this line does not exist in reality. This is just drawn, okay, to show you. Now let me explain to you what horizon is. See, if you climb up to a uphill, and then suppose say around you there is vast plain, okay, plain, plain, then how will you see? Okay, the landscape before you, okay, it will look like this. Here, since below you it is vast plain, it will appear to you as if the sky and the land, they appear to touch each other. So the point, okay, the point where the sky appears to touch the land, the ground, is called the horizon. So that is what is called the horizon. Okay, so the horizon is the point where the sky appears to be touching the ground. That is called the horizon. Now remember, class, one thing, that we only see things above the horizon. Okay, above the horizon you will see. Below the horizon we don't see. So remember, below the horizon we don't see. Okay, so below horizon we do not see. Okay, so we do not see the things below the horizon. Okay, so we only see things above the horizon. All right, now our Earth is here. Now this is not a good picture of the Earth. This is an incomplete picture because I have not drawn the atmosphere. So I have to draw atmosphere because we have atmosphere, isn't it? So we are blanketed by an atmosphere. So let me draw the atmosphere now. So let's say this is the atmosphere covering our Earth. So let's draw this atmosphere. Okay, so this is our atmosphere. I hope it is visible. Okay, I am just drawing. Okay, I hope it's visible. Yes. So now let us take an observer here. So observer is here, and what is he gonna do? He will wake up early today. Why? Because he wants to see the sunrise. Okay, so he wants to see the sunrise. So he is looking in this direction. Okay, in this direction. Let's say this is the east. So this is the east. So he knows very well that the sun rises from the east. So he's looking in this direction. Okay, so he wants to see sunrise. So he wakes up early and then he's looking towards the east. Now the sun is still here below the horizon. So the sun is here. The sun is here. So this is the sun. The sun is here. So the sun is below the horizon. So if I ask you, has sunrise taken place? What will be your answer? Yes or no? The answer is no. Okay, because the sun is below the horizon, sunrise has not taken place. Okay, remember that the sun is below the horizon, so actual sunrise, okay, has not taken place. The sun is yet to, okay, rise again. The sun is yet to rise. We will only say the sun has risen when it crosses the horizon. Okay, since it's below the horizon, remember, at this position sunrise has not taken place. But this is the sun, so there are constantly rays coming out of the sun. So let us draw the sun rays. Now the rays are traveling into the space, okay, like this. Okay, now most of the rays, they are going out of the space. They are going out in the space, but some rays, okay, they interact with the Earth atmosphere. And so what happens? These rays, okay, which interact with the atmosphere, they undergo bending. So they will not travel like this, rather they will undergo bending, and then these bended light rays will enter the eye of the observer. So let us make him a little taller. So these refracted rays, they will enter the eye of the observer, and then these refracted rays will bring the image of the sun to the observer. So now this observer will see the sun. Interesting, isn't it? So the observer is able to see the sun, whereas the actual sun is still below the horizon. This is the meaning of advanced sunrise. So though the sun is below the horizon, okay, because of these refracted rays, okay, the rays which enter the Earth atmosphere and they underwent bending, okay, now these rays, they bended and then they have entered the eye of the observer. So now the observer, okay, these refracted rays will bring the image of the sun, and now to the observer the sun becomes visible. Okay, so this is the apparent position of the sun. Remember, okay, earlier we were discussing about apparent position and actual position. This is the actual position of the sun, class, but this is the apparent position of the sun because of refraction. Okay, so the sun, okay, the sun is visible to the observer, okay, though there is still some time for the, okay, sun, okay, the sun will still take some few minutes, okay, I'll tell you later how much minutes, but the sun will still take some few minutes, okay, to rise above the horizon, but the observer will start seeing the sun. This is called advanced sunrise. Okay, now the sun will rise up, and then the sun will continue its journey, and then finally at one point the sun will set. So now time for the sun to set. So now the sun will be said to have set when it has gone below the horizon. So same thing, the sun is here now, okay, the sun is here, it is below the horizon, so the sun has actually set. Okay, but again, what happened earlier in the morning will again happen here, since there are billions and billions of rays coming out of the sun. So still, okay, though some rays, they will go out into the space, some rays will again interact with the earth atmosphere, okay, and then they will find their way to the observer's eye again. So these refracted rays which enter the eye of the observer will again bring the image of the sun. So the sun is still here again, so the sun is still visible to the observer, okay, whereas the sun is actually set, okay, the sun has actually gone below the horizon. That means sunset has taken place but then the observer is still able to see the sun. So this is called delayed sunset, because the observer gets to see the sun. Okay, this is called delayed sunset. Here it is called advanced sunrise, because the observer gets to see the sun advance. And this is called delayed sunset because the observer still gets to see the sun, though the sun has actually set. Okay, the sun has actually gone below the horizon, which should be invisible, but it is still visible because of refraction. The light rays coming out of the sun from the setted sun undergoes refraction through the earth atmosphere, and then these refracted rays, they bring the image of the sun to the observer, and that's how the observer still gets to see the sun. So remember, this observer is us. We are the observer. This phenomenon happens to us every day. Okay, if you are an early riser and you get to see the sunrise, remember this phenomenon is happening. If you love sunsets and you make sure that you watch the sunset, this is happening to you. So now through this phenomena, okay, we get plus 2 minutes extra, okay, and then through this phenomena, same here, okay, here also we get plus 2 minutes extra. So we get to see the sun 2 minutes early, okay, 2 minutes early, and then we get to see the sun, okay, 2 minutes later, okay, after the sunset also. So 2 minutes early before the sunrise, and 2 minutes later after the sunset. All right, so all together in a day we get 4 minutes extra sun, or daytime, we can say 4 minutes extra daytime. Interesting, isn't it? Okay, the atmospheric refraction, such a wonderful phenomena. Okay, it helps us receive 4 minutes of extra sun. Okay, so we get 4 minutes of extra daytime because of this phenomena. Okay, now one more fact I'll tell you, one more interesting fact I'll tell you, which is not mentioned in the textbook, but it was there in the old textbook, which is at one point of time, okay, at one point of time, the apparent position and the actual position, they will coincide. What position do you think it will be, class? What position do you think it will be? The position will be at 12 noon. At 12 noon, the sun will be just right above your head. Okay, so at 12 noon, what happens? The sun will be here. Okay, and when the sun is here, at this very position, which will happen exactly at 12 noon, okay, 12 noon, Okay, there is no apparent position. Okay, the apparent position and the actual position are same at this time. Okay, when the sun is just right above your head. So basically, I can show you one picture here. So let's say this is the real sun and this is the apparent sun. So as it continues its journey, what happened? The distance between the apparent sun and the actual sun gets lesser and lesser, and then at this point they overlap. Okay, and so here there is no apparent position or actual position. No, there is no apparent position, only actual position. And again, as it continues its journey towards the west, again the gap goes on increasing. So it should be like this, because this is the actual sun. So the actual sun will move ahead and the apparent position will keep on going like this. And at this point, you see, okay, the below one is the actual sun. Okay, and this is the apparent position. All right, so that's how it goes. So this is it, class. So I have explained to you. Okay, this is a very interesting topic. So I hope you have understood. Before I go, I have a question for you. So let me erase this one and then ask you the question. Now earlier in the video, I have explained to you about our Earth. Let this be the diagram. Our Earth is here. Then these are the different atmospheric layers. Okay, 1, 2, and 3. Okay, so the question is, which of the 3 layers has the highest Ri? This is the question. All right, so this is Earth. Remember, this is Earth. Let me draw some trees for you, so that, and let me even draw a house for you. Okay, don't laugh at my house. Okay, again, one more tree for you. Okay, so this is the layer of atmosphere closest to the Earth, then layer above it, and basically this is space. Okay, now you tell me which of these 3 layers has the highest Ri. Which of these 3 layers will have the highest Ri? Please comment the answer in the comment box. So class, with this I'll end the video. This video has rather been long, but then it is worth watching. So I'll see you again in the next video.